What is a nullifying polynomial? Okay, nullifying polynomial is essentially this one. But let's start from a starting point because it's very important here. If I've got a matrix that is n times n, those ones live in a finite space, finite dimensional space. If I have A1, 1, A1, 2, A2, 2, A2, A2, 1, A2, 2, how many parameters do you see here? 4. This matrix lives in a 4-dimensional space. True? Are we together? Think of it. I take the matrix and I take those two and I stack them down there. True? Isn't it a 4-dimensional vector? And if I have column, I take this one and put it here, this one I put it here. Whenever I've got n times n, for sure, at most, n times n squared, is kind of the dimension of the space that somehow I made a mistake here. Here putting you Kelly Hamilton is kind of wrong. I remanaged the slides and then I didn't realize that I was kind of using some part. This one is finite dimensional. It means that there exists a basis of matrices for which any A is going to be built as a linear combination of those base matrices. Base matrices for the 2 times 2 is going to be 0, 1, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. This is one basis. Of course, you might have other bases. Do you see it, people 1, 2, 3? I see a very puzzled face there. Why are you very puzzled? It was a very puzzled. It was seeming a puzzled faces. If I have 7, 9, 11 minus 2, this is going to be 7 this stuff plus 11 this stuff plus 9 this stuff minus 2 this stuff. We are together? Perfect. Ignore this stuff here. I will remove it from the side. Let's take a polynomial and let's see how a polynomial might actually be a function on the matrix. So, if I take the polynomial P of S equals to S plus 3, S plus 2. This one is going to be equal to S squared plus 5S plus 6. Together up to now? Now, let's put A equals to 1, 3, 7, 9, 10, minus 11, 0, 0, 1. If I take this one and I consider A squared, that will be something. I might put here, I might put P of A and write P of A as A squared 5A 6I. Together? See how you can construct a matrix starting from a polynomial. Okay? This is going to be a matrix. This is going to be some number. True? Are we together? Here there's no S. Whenever I take P of A, specific P of S, will have a certain structure. I plug in A, I get a matrix. Together? If I'm lucky enough, given some coefficient that define the polynomial, P of A is going to be equal to 0. You might not trust me, so we do a numerical example now, and then you will see how this is actually essential for us. So we take the matrix 1, 1, 0, 1, and then my characteristic polynomial is going to be s minus 1 squared, that is going to be equal to s squared minus 2s plus 1, true? Are we together to this? Now, this one squared is going to be equal to 1, 1, 2, 1, 0, this one. Madonna Santa Benedetta. I've got to write it. You see how my neurons are basically decaying. So, first element is going to be this times this. It's going to be 1. Then I have this times this, 2. Then I have this times this, that is 0. Correct me if I'm wrong, people. If I do some mistake, I'm going to be in a mess. Well, I could have of course I could have computed it I'm dumb. Anyway, you will understand why I'm dumb whenever we will do Jordan mini blocks. Anyway, that means that I have 1, 2, 0, 1 minus 2, 2, 0, 2 plus 1, 0, 0, 1. True, this one becomes the identity together. Are you following me, people? 1, 2, 3. 4? Where is a 4? So, yeah, 4. Bravo. And then I've got some mistake somewhere. No, it's 2. No, it's a 2. It's a 2 because it's S. 2S. Yeah. You were trying to trick me, true? Let's do the computation. 1 minus 2 plus 1, 0. 2 minus 2 plus 0, 0. 0, 0, 0, 0. 1 minus 2 plus 1, 0. Okay. Very interesting. Remember characteristic polynomial. Characteristic polynomial will always nullify. Anyway, let's go back here. P of S, generic S, the generic P. P of A, depending on A, I might get 0 or not. True? If I was putting this stuff here, if I was putting this stuff here is going to be something different. If I was taking this A, plugging here this A, we would get something different from 0. Okay? I guarantee you. And you will understand why. And as a metacognition, as a self-assessment, now you don't see it why, but later on, whenever we will see that the characteristic polynomial of this one, it's not this one, it will be clear why it has to be different from 0. Okay? You will need to arrive at this point of understanding what I'm saying right now, that you do not understand now. In 3 weeks, you shall be able to understand. Okay? Perfect. So, generic P, generic A. If we are lucky, we get 0. How much are we together up to now, people? Perfect. If the couple A, P of S is such that we are lucky, then we say that P nullifies that A. Okay? And actually, very interesting, if I have a P that nullifies A and I take a change of basis, it means that instead of this, I take this one. Instead of this, I take this one. Instead of this, I take this one. I can take all the T's out and I re-get this stuff here. That means that if P nullifies a certain A, actually it nullifies all the A's that are the description of that calligraphic A. Okay? So, nullifying, the fact that a polynomial nullifies a certain specific matrix, capital A, is actually because that polynomial nullifies the physical phenomenon that gives us the calligraphic A. Watch out. What does this stuff here mean? So this might not be kind of clear what a polynomial is. Let's go back here. This one takes the Mona Lisa and does something to the Mona Lisa, true? Together? If I take 0.7, this stuff here, it means Mona Lisa, and then I shrink it a little bit. True? Together? If I take this one and I do it squared, so I do it squared, sorry. What am I doing? I'm taking the Mona Lisa, transforming, then taking this one and transforming it again with the same transformation. Doing twice. True? Now you see, and of course, if I take this one plus this one squared, I'm taking the Mona Lisa and transforming. I'm taking the same Mona Lisa, transforming twice. I get, I don't know, something like this. And I take the sum of those two. Okay? Together? You get twice Mona Lisa, but they are like two images, one distorted once and one distorted twice. And of course, if I got this plus 0.7, this one means that the second one, I'm kind of shrinking it. How much are we together, people? 1, 2, 3. Are we together on how to interpret this polynomial in terms of combination of linear transformations? If P of A equals to 0, it means that I'm taking combinations such that the whole Mona Lisa eventually, if I apply everything, goes where? Disappears. And that's the meaning. P nullifies A because in a certain sense it annihilates the transformation. How much are we together, people? 1, 2, 3. And of course, it's a property that is a property of calligraphic A. Because the P of S means combining the calligraphic A, true? And if I give a certain specific name that is the capital A, well, the physical phenomenon is that I combine transformations in an opportune way, okay, such that the whole Mona Lisa goes to a point. If I call calligraphic A with a certain basis or another basis or another basis, the physical phenomenon is the same. This means that this has to happen. Okay, people, are we together, people? For any square matrix A, its characteristic polynomial nullifies A. What was I doing before? I was a little bit sneaky. I was taking 1, 2, 0, 1, and I was computing this one that is S minus 1 squared. True? And I know that this one, that is the characteristic polynomial of this one, is going to nullify this one. Very, very informally, very extremely informally. This is not the right proof. We will see Cayley-Hamilton theorem. If I take here and take instead of S, I put A, what do I get? It's determinant of 0. True? It's not the right proof because this one is a polynomial, this one is not a matrix, so it's not the right proof. But this is kind of something that makes you remember this. Let's see. Discuss, people. You have to chat. People, what would you say? I hope that everybody says 3. Every matrix has the characteristic polynomial, true? The characteristic polynomial, we know it's nullifying. So every matrix has at least one. We will see that it has many, actually. Perfect. This one might seem like correct, but it's wrong in general because this is only if my matrix has real coefficients. But if I start with a matrix A that has got complex coefficients, the nullifying polynomial is going to have complex coefficients. Okay? Are we together, people? 1, 2, 3. How are we? Are there questions?